Page. Calculus of vector functions, determine the derivative. Can you guys take a derivative? You guys want to look at the derivative of this stuff? Can we do derivatives?
Yeah.
Okay. The first derivative is fine. The next one's a little bit harder because it wants you to find t of 1 as capital T. Some of you don't know what this means. Some of you might. Some of you are like, oh, no, I'm a little iffy about it. I'll let you guys do the first one on your own, but we skip straight to the t of 1 one. This one says r of t equals, what is it? T squared, 3t squared, something?
3t, 2t squared, and t cubed.
So I want to find t of 1. That means I need to find r prime of 1 and divide by its magnitude. Let's find r prime of 1. First derivative would be 3, 4t, 3t squared. Plugging in 1 gives me 3, 4, 3. This is not quite t yet, this is merely r prime of 1. So I'm going to
what does the capital T mean?
It means the unit tangent vector. So let's go over here to this guy. When we're talking about the direction of motion, the tangent vector is this guy. It's kind of like if ever I find the slope of a line tangent to a curve.
So
That's what you learn in Calc 1, how to find a line tangent to a curve. R prime gives you just some vector that is tangent to it. Now it turns out the longer r prime, the faster that curve is moving as time passes. So if this was say 30, 40, 30, then that thing's moving pretty quick as compared to 3, 4, 3. When we're concerned merely for the direction, we make it a unit vector. Sometimes we say we normalize it just because we care about the direction. We don't care so much about the speed at that point. So that's what we're doing by dividing by the magnitude. We divide by the square root of 9 plus 16 plus 9, which would be 34. Cool? So t of 1 would equal 3, 4, 3. You say 3 over root 34, comma 4 over root 34, comma 3 over root 34. And t will always be a unit vector. Pretty easy as long as you know the definition. It's pretty easy to compute based on a definition. The velocity of an Alabama, this is great because, so if anybody went to my Calc, or Jordan's Calc 3 review at Study Edge, they saw a problem that was like the velocity of an FSU student's rejection letter. Now because I'm bound by a certain copyright and I've signed away my right to those materials, I have to tweak small things so I'm not plagiarizing. So I made it in Alabama in memoriam of this past weekend. So the velocity of an Alabama student's rejection letter from UF is v of t equals 2t comma negative 6 sine t comma 2 tangent t plus pi over 4. Determine the position function for the letter r of t if the initial position is 2, 1, ln of 2. So velocity is the derivative of position. So we're going to integrate that first guy. I'm going to integrate r prime of t. The integral of 2t is t squared. Integral of negative 6 sine 3t would be 2 cosine 3t. And the integral of this third guy, what is the integral of tangent of t plus pi over 4? I wouldn't blame you if you forgot this one, but Kieran might throw a weird integral like this since that you learned in way at the beginning of Calc 2, right? The integral of tangent is ln of secant. So it's been a while since we've seen that though, right? I might recommend there's two there. Buffing up on your integrals like ln or integral of tangent, integral of secant, integrals cosecant, integral of cotangent, stuff like that. Okay. Keep in mind that whenever you integrate, you have to say what? Anytime it's an indefinite integral. What's that? Well, there aren't any bounds here. So if it's a boundless integral, if it's an indefinite integral, if it's an indefinite integral, you have plus c. But this would be not plus the number c plus a vector c, which we'll denote by cx, cy, cz. So we're told the initial position of such a letter is 2, 1, ln of 2. So when I plug in 0 to this, I should get 2, 1, ln of 2. When I plug in 0 here, I get 0, 2, 2 ln of 0 plus pi over 4 is pi over 4. The secant of that would be root 2. I'll save you the time to just tell you the secant of pi over 4 is root 2. And we're going to say, when we add this c vector, cx, cy, cz, it should equal 2, 1, ln of 2. Right? 2, 1, ln of 2? Okay. what should cx be so that when it's added to 0 it gives me 2? 2. What should cy be so that when it's added to 2 it gives me 1? Negative 1. And this is the hard one. What should cz be so that when it's added to 2 ln of 2 it gives me ln of 2? I'll be really impressed. Take a stab in the dark, Thomas.
I was gonna say like divided by ln of 2 or something.
Go with your usual good.
0.
Yes. It's 0. Okay, so why is it 0? Remember, square root of 2 can be written as what? 2 to what power? 1/2, right? Square root of 2 can be written as 2 to the 1/2. What can I do with that 1/2? It's the power of an argument of a log.
Bring it down.
Bring it down as a coefficient. What's 1/2 times 2? 1. And I have that right there. So I don't need CZ to be anything but 0. Cool? Make sure you know your log rules so that you don't get messed up by that. Like that. Good? Or just get 0. Good? Alright. Last one. 4t cubed, t cosine of t squared, t cosine t. This was good because it's going to showcase 2 different methods of integration that you guys have probably haven't seen in a while. It'd probably be good for you to, it would be good exercise of integration. What, 0 to pi?
Yep.
Okay, it's the integral of 4t cubed. That's a piece of cake. That's just 2 to the 4th. What's the integral of t cosine t squared? What technique of integration would you use to integrate that?
It's u sub.
It is a u sub. You would say u is equal to t squared, du is equal to 2t dt. This transforms the integral into integral of 1/2 cosine of u du. If you perform the u sub correctly, this will transform into that. Does that sound good? Does anyone want me to show you some of the steps? No problem doing it if you want me to. Yeah? Okay. So we have u is equal to t squared. I'm going to replace that t squared by a u. Remember, we need to solve for dt up here. So dt equals du over 2t. I'm going to replace the dt, this would be a dt here. I'm going to replace that dt with du over 2t. Notice the t's drop out, which makes us really happy. That t is going to cancel with that t. So indeed, I get 1/2 cosine u t, the integral of which would be 1/2 sine u. But instead of saying 1/2 sine u, we're going to say 1/2 sine of t squared, which was our original substitution. The next integration here is not u sub. What technique of integration do I need to do here? What's the next technique of integration you learn in Calc 2?
Integration by parts.
By parts. I don't imagine you'll have a trig sub or a trig integral or a partial fraction decomposition. I think the worst type of integration problem you'll ever see is an integration by parts. So make sure you buff up on that, which we'll do now. We're going to actually use tabular method. In the tabular method, when you have some polynomial like t squared, t cubed, t to the 4th, whatever, times a trig like cosine or sine or e to the x, or e to the t, you put polynomial on the left, and you put the transcendental function, which is cosine or sine or e to the t, on the right. You differentiate down this column. Derivative of that is, okay, we can stop at that point. Integral this, then we integrate this column. So you can say derivative this column, and integrate this column. Integral of cosine is sine. Integral of sine is negative cosine. You can go one more time if you'd like, but not necessary. Alright. We draw diagonals. And make sure. Right. Alternating sign starting with a plus sign. Is this familiar? Okay. So this would give us t sine t plus cosine t. So this is our integral. Notice that we do not need to say plus c because this is a definite integral. By definite integral, I mean we have bounds. So it merely means we plug in the upper bound, plug in the lower bound, and find the difference. Plugging in pi gives me pi to the 4th, comma, pi squared. Sine of pi squared. Okay. Does anyone? What is sine of pi squared? This is where I make the joke. It's approximately, I have no fucking clue, right? It's not on my unit circle, so I have no idea what that's going to be. Comma, plug in pi here, sine of pi is 0, cosine of pi is -1. Minus what you get when you plug in 0. When I plug in 0 here, I get 0. When I plug in 0 here, I get 0. When I plug in 0 here, I get 0 plus cosine of 0, which is 1. So I get a final answer of pi squared, or pi left together, comma 1/2 sine of pi squared. -1 minus 1 is -2, and that's your answer. As far as the geometric interpretation of that answer, don't worry about it. What does that mean? I don't even know. Don't even know. Okay. Give a parameterization for the curve forming the intersection of 3x plus 2y equals z squared and 2z equals 3y minus 1. Thomas, you told me earlier that you don't need to memorize the several different quadratic surfaces. Was this something mentioned in class that you do not need to memorize the quadratic surfaces like paraboloid, hyperboloid of one sheet, so you don't need to know these, you don't need to memorize them? Okay, that's good. We're not going to turn the page though, there's still a little bit stuff we can do that doesn't have to do with that, but we might have to skip a couple, we can skip a few, maybe. Plane was what? 3x plus 2y equals z squared. That's not a plane at all. 3x plus 2y equals z squared. And 2z equals 3y minus 1. 2z equals 3y minus 1. Okay.
In the studiers, this is all he went over just because
Yeah.
the guy said that.
Good to know. That's actually a graphic that I drew. I drew that by hand. Fucking with you. I didn't.
That's what he said. That bastard.
No. That'd be good. But I think I just copied that from a textbook. Looks really good though. I mean, mine. Okay. So when I want to parameterize a curve, I usually let one of my variables, either x or y or z, equal t. And usually in one of the equations that is simpler. This has all three variables, so I'm not going to use that. Over here, I'm going to let y equal t. Just let y equal t. Now by letting y equal t, I can easily solve for z. Z would then be 3, you can say 3y minus 1, but since we know y is equal to t, it would be 3t minus 1 over 2. What would x then be? Well, now that I know that y is t, and z equals 3t minus 1 over 2, I'm going to plug these guys in here and solve for by what x is.
Because that matrix is very simple.
I just went ahead and squared this out. 3t minus 1 over 2 squared gives me 9t squared minus 6t plus 1 all over 4. I'm going to subtract 2t from both sides. (2t) is the same as 8t over 4, and if I take 8 away from 6, negative 6, I get negative 14. And then divide both sides by 3. I get 12. So that's what x is. Y, z, and x. And that would be a fine curve parameterization. So you let one of either x, y, or z be t. Let one of x, y, or z. Let one of them be t. And then that gives you can then solve for the other variables based on that. Unless it happens to be the case that your shapes are maybe circular in nature, as in the case of the next problem. Next one would be x squared plus y squared equals 25, and x plus 2y plus z equals 4. In this case, because I have x squared plus y squared equals 25, x plus 2y plus z equals 4, I might instead want to use, again, because I have this circular shape, I might instead want to use sines and cosines. So that's what I'm going to do here. Rather than let one of my variables either be, rather than let one of my variables x or y or z be t, I'm going to let x and y be the usual trig ratios that I let them be when I have a something circular nature. So you can write something circular, you can circle the x squared plus y squared equals 25, and say I might want to do something like this. It's a circle with radius 5, so I'm going to use 5 cosine t and 5 sine t. And now that I know what these are, hey look, I can go plug these in over here and figure out what z is. Z is equal to 4 minus 5 cosine t minus 2y, which would be 10 and sine t. Make sense? X is 5 cosine t, y is 5 sine t, z is this. This is actually not that hard to actually memorize, or what shape this would be. What shape is this? I mean, I play this game I would always play this game with every semester with all my Calc 3 students, and I would just fucking hate it. What'd you say? See, yeah, this is what, no. Not a line.
Wait, that one?
This guy here?
Which one?
This guy.
How's that not a line?
It looks like a line, right? Because you think x plus 3y equals 5 is a line. We dealt with this for like 15 minutes earlier. Explain.
God damn it.
It looks like a line. I can understand why you say line, because you know that. Back in pre-calc, what was that? That's a line. So this should be a line, right? It's plain. Remember, what do the lines look like? It's x equals y equals z equals 3t plus 4, 5t plus 9, negative 3t minus 4. Okay, this is a plane. What is this? It's not a circle. It's a circle, and again, in pre-calc, it's a circle. But in space, this is it's almost not quite a helix, a cylinder. So what are you trying to draw the cylinder? This is a cylinder of radius.
Because it doesn't have a z coordinate?
It doesn't have a z coordinate. In fact, anything that's missing a z, or if it's missing the variable z or y or x, it's a cylinder that is parallel to the missing axis. So, cylinder. And then this is some plane that comes through and cuts it like that. And you actually get an ellipse. If you took a toilet paper tube and cut it at an angle, you get a cross-sectional shape that looks like an ellipse. I don't have those things on me, but those would be good props. Okay? Alright, that's the parameterization. X equals 5 cosine t, y equals 5 sine t, and z equals that. And again, you either let x or y or z be t, or you, depending if you're given something circular in nature, you use that sine and cosine trick. Give a parameterization for the curve formed by, this one you could do on your own. Let's do the last one though. And we'll skip these. We'll skip these for now. We'll just do those later if you guys want to. But they're not too big a deal. I don't know if they're going to show up. Okay. Arc length and natural parameterization. That's the arc length formula. That actually looks, if you cover up the dz dt squared, it looks just like the arc length formula you learned in Calc 2, right? It's just got an extra component. So, find the arc length of 3t squared plus 1. 2t cubed minus 7 or some shit? Doesn't matter. Comma, and then what, t or 1? 7. So that's our vector function. We want to figure out how long the curve is. How long the curve is from t equals 0 to 1? Yeah. 0 to 1. Integrate 0 to 1. Square root of? What's the derivative of this guy?
6t.
6t. What's the derivative of this guy?
6t squared.
6t squared.
Come on,
6t squared
let's not play this game.
squared. What's up?
Let's not play this game.
What's the derivative of 7? 0. Okay, so then we have dt. I have to make a little bit of work of this. This is 36t squared plus 36t to the 4th. What can I pull out of this? This is where I always make sure you always pull out, guys. What can you pull out of the square root? 36t squared. 36t squared will come out, making it 6t square root of. And because I pulled 36t squared out, I'm left with a 1 and a t squared left over here. What technique of integration do I use to tackle this? It's another use of. We're going to say, go gadget, hand erase. Okay, u equals t squared plus 1, du is equal to 2t dt, and therefore dt is equal to du divided by 2t. This makes your integral look like this now. 6t square root of u times du over 2t from 0 to 1. Replace the t squared plus 1 by u. Replace the dt by du over 2t. If you cancel the 2t and the 6t, you're left with just the integral of 3u. I'll say 3u to the 1/2 because it will make it easier for me to apply that inverse power rule, reverse power rule by writing it like that. When I integrate, I get 2u to the 3/2. Make sure you back sub. Still on camera? Yes, ma'am. Backs up. And we get 2 times t squared plus 1 to the 3 halves. Plug in 1, plug in 0, find the difference. When I plug in 1, I get 2 times 1 squared plus 1 is 2, 2 to the 3 halves minus 2 times 0 plus 1 is 1 to the 3 halves.
So what's the problem? 9. 9y double prime.
Oh, okay, 9y double prime.
Something else you might want to write down.
Plus 25y.
X to the 3 halves is x root x. Makes things easy. So whenever I see 2 to the 3 halves, it's the same thing as 2 root 2. So I have 2 times 2 root 2. 2 times 2 root 2 is 4 root 2.
Draw the characteristic equation by using the substitution.
Minus 2. 1 of the 3 halves is 1. Minus 1 minus 2. This is your arc length.
This isn't like just substituting r. Why can't you just do y double?
We're also going to talk about the natural parameterization or the arc length parameterization. Have you ever referred to it as the, have you heard the term natural parameterization in class? Maybe. I might have tuned it out because not much of it makes sense. I'll explain it to you in a second.
Because you're really, you're substituting this y equals b r, so y prime would be r.
Imagine yourself at your house or your apartment or your dorm, whatever.
So it's the same.
You could start driving west. Okay, start actually, well, you wouldn't go too far. So you start driving kind of northwest, right? You start driving northwest, and I say, where are you after 5 hours, right? You can figure out where you are after 5 hours, knowing your rate of speed and how long you are after 5 hours. So I could say, where are you after 5 hours? You might say you're in Atlanta or something, right? I could also ask you, where are you after 500 miles, right? These are similar questions that I'm asking you where you are, but instead of asking you where you are after a given amount of time, I'm asking you where you are after a given amount of distance. That's the idea behind the natural parameterization. So here we have, determine the natural parameterization for the curve r of t. 2 cosine t minus 1, 3 minus 2 cosine t.
So substituting in the characteristic equation.
Okay. So it's a 2-dimensional vector.
Plus 25.
Here's how you find the natural parameterization. Here's what you do. You say S equals integral from typically 0. It'll give you the starting value, but we'll say 0 to t.
Minus 5 equals 0. Such that
0 to t, we're going to use our arc length formula. Now be careful here. For the purposes of this arc length formula, we shouldn't be using t because it's one of our bounds. We're going to use u instead. So what's the derivative of this guy?
So the first solution to our equation.
Negative 2 sine t. Let's say sine u.
5x. That's y.
What's the derivative of this guy?
Wait, is it 3r minus 1 squared?
Negative 2 cosine u squared. We'll say d.
So
This is really nice because negative 2 sine u squared plus negative 2 sine cosine u squared gives you
Which is how we get that. That's our first solution.
square root of 4. 4 sine squared plus 4 cosine squared. And don't fuck this up, by the way.
Got that? We don't have to do that reduction order.
What is 4 sine squared plus 4 cosine squared?
not really. I mean, it'll come back.
4, not 8. A lot of people would say 4 plus 4. Hey, that's 8, right? No, it's 4. Okay. 4 sine squared plus 4 cosine squared is 4, not 8. So I guess the square root of 4 to u.
It's going to be function. It's going to be our first solution times some function of x. So we're going to run the substitution. Y equals
What's the integral of 2 to u? That should be 2 u.
times y1.
Wait, why is there?
2t minus 2. So we have, here's what we end up with. S equals 2t.
Because it's how you derive. Somehow for two real roots, when the roots are the same, it's e to the
Solve for, this is what you solve for s.
plus we get two real roots. We're deriving y, you do plus q.
And now, ready for the arc length parameterization? Instead of this, we're going to say this.
You have one term plus another. And each term is a solution to the equation. But since the equation equals 0, you just leave So we're gonna say y2 is some
I've replaced every instance of t by s over 2.
such that y2
So this is what's called the natural parameterization. That is how you find it.
y1 plus u times y1 prime. And then y2 prime equals u double
We have 2
prime
pages left, I think.
y1 plus 2u prime y2.
Nice. I thought she wasn't who she. I thought she wasn't who you thought. Who she thought.
Now we're gonna
I was like, I'm walking away now. Really
the
are.
original equation, so we have 9
What's the next page? Curvature.
plus 2
Just follow the formulas. By the way, to correct everything here, it says
u y double prime.
it says absolute value. Technically, because t is a vector and you take its derivative, it should be. As far as I'm concerned, I think it should be. Well, magnitude. Oh, it's a tough question. Double check with Kieran. He uses a single, or at least in one of his tests, but he counted it as right. So I have to double check my. No, it should be double bar. It's a magnitude because it's a vector. We're talking about a vector. You got vectors. You don't take the absolute value of vectors. You take the magnitude of vectors. So, like for instance, I said -3. What's the absolute value of -3? 3, right? That doesn't make sense, right? You don't. That's a magnitude operation. What's the magnitude of the number? It doesn't make sense. So you definitely need a vector there. Much the same way, I can't leave this without double bars. Keep in mind that on one of his tests, he left it without double bars. He did the single bars, and he counted it as something that was true. And it should be false if you do it in single bars. It's a magnitude, so you should be using double bars. Ask him in class if you can use double bars and single bars interchangeably. And on a test, if he says something, if he gives you a vector quantity that doesn't have double bar in its magnitude and instead has single bars, that can't be right. It's not possible to do that. Unless he says they can be used interchangeably. Anyway, that formula should say double bar dt ds. All right. Determine the curvature of r of t equals 3t squared plus 1, 2t cubed minus 1, 7 at t equals 1. I don't know if I'm going to enjoy doing this. Here we go. We're going to take r prime and r prime of t, double prime. Actually, r prime of t was what? 6t squared, 6t cubed, comma, 0. Yes, at t equals 1. So this gives me 6, 6, 0. I think I meant to change these numbers. I didn't do that. And then r double prime of t, should be a 1 rather, would be 12t, 18t squared, 0. So r double prime of 1 would be 12, 18, 0. Okay.
Andrew, I'm confused how you got R prime of t with 6t.
Did I fuck up? Oh, just 16.
So
And then that should be
Yes.
Yeah.
Whoops.
pretty much clean it up. So we left with u double
Try that all over again.
plus
6, 12t. That's much better. 6, 12, 0. So 6, 6, 0 and 6, 12, 0. We're going to cross these vectors. That's what the curvature formula calls for. 6, 6, 0, 6, 12, 0.
30 over 9.
That would be 0i plus 0j. 72 minus 36 is 36k. Okay?
Equals 0.
So this is r prime cross r double prime. And according to the curvature formula, you want to find the magnitude of r prime cross r double prime.
y2
Fun fact, what is the magnitude of the vector 0, 0, a? What's the magnitude of the vector 0, 0, a?
A.
A. Actually, technically, absolute value of a, because a could be negative, right? If it was 0, 0, negative 3, the magnitude wouldn't be negative 3, but positive 3. But yeah, it's just the number or whatever that is. This is going to be 36, right? Divided by the magnitude of r prime. What is the magnitude of this guy? 660. What's the magnitude of that? Have a guess. If you know if it's 666, the magnitude would be a root 3 or 6 root 3, right? Because it's 660, it's not going to be 6 root 2, yes. So it'd be
where we'll say where we'll
6 root 2.
We'll say
Fuck you. It's going to give me 36 over 6 cubed times 2 root 2, which gives me 1 over
It's
12 over 2. That's the curvature. Last thing is determine the curvature of r of t equals 2 cosine t, 3t, 2 sine t. This one's kind of annoying because I didn't did I specify at a particular point that I say at 4 or at t equals 0? I didn't do that. That makes it a little more nightmarish than usual. So 2 cosine t, 3t, 2 sine t.
So I'm substituting e to the 5x over 3 for y1. So that's e to the
Okay.
yeah. Times e
Okay.
raised to the integral of
Because I didn't give you a particular value of t, you're gonna have to do this all in terms of t. You don't get to plug in a number, right? Because our answer might be in terms of t. The nice thing about this is that the helix is constant
That should
curvature,
be
but
3t.
3t. Thank you.
e raised to 0 1. This step right here. Because this only works when you
There's our prime. There's our double prime. We're gonna cross those. Hey, it's a good thing I wrote them stacked like that because IJK go right across the top of this. IJK. So crossing these gives me
from the u double prime.
negative 6 sine t.
So you have to run the substitution.
Bear with me here. Watch this. What's negative 2 sine t times negative 2 sine t? Positive 4 sine squared. What's 2 cosine t times negative 2 cosine t? That's negative 4 cosine squared, but this is a back diagonal, so you're going to subtract it. It's going to be plus 4 cosine squared. What's 4 sine squared plus 4 cosine squared? 4. 4. Don't tell me and say 8. Yeah, 4, right? Good. And then this time this is 0, 3 times this is going to be negative 6 cosine. It's going to become a plus 6 cosine. 6 cosine. Okay. We'll get the magnitude of that in just a second. Actually, we'll get it now. Actually, if I ran really quick about that. This would be 36 sine squared plus 16 plus 36 cosine squared. What's 36 sine squared plus 36 cosine squared? 36 plus 16 would be how many cards in a deck? 52. Okay. Now we have to do
So we said it equals 1.
curvature equals this guy over the magnitude of r prime cubed. Now here's r prime. Let's square this guy. What's negative 2 sine squared squared? It's going to be 4 sine squared plus 9 plus 2 cosine squared squared, or 2 cosine t squared. That'd be 4 sine squared plus 4 cosine squared. What's 4 sine squared plus 4 cosine squared? It's 4.
So that's how we get
Plus 9 gives me what?
Rad 13.
Yeah, radical 13. Should I slow that down? Does anyone want to repeat some steps here? Am I losing anyone? Okay. All I'm doing is squaring all this guys, adding them up. 4 sine squared plus 9 plus 4 cosine squared. I get some sines and cosine squares that combine to make 4, so I get 4 plus 9, 13. And I need to cube this guy. So this is, by the way, 52. 52 card deck has 4 suits, so you can pull that 4 out as a 2. 2 squares of 13. 4 suits of how many cards each? 13, right? Ace through king. Ace is low, ace 2, 3, 4, 10, jack, queen, king. So root 52 is 2 root 13. 3 root 13 cubed is 13 root 13. Right, that's that trick. If I have a number x to the 3 halves, it's x root x, which is what this is. This is 13 to the 3 halves. What happens here? These root 13s cancel. So my curvature is a constant 2 over 13. That will always happen for a helix. A helix always has constant curvature. So it doesn't matter what value of t that you're at, the helix will always have the same curvature at every point. That's why they will give one like this. Is why they'll give one to you like this, because the sine squares and the cosine squares combine in such a harmonious way that they don't give you ugly numbers. Although some of you say, I don't know what you mean. How's that not ugly? There are worse. Okay, next page.